Hello, everybody. Happy Friday. This is the COVID-19 edition. We are in lockdown. We're trapped in a radar detector lab together.
There are worse places to be.
There are with worse people.
Yeah, I mean, granted, there is COVID here, but you know what else we have?
Water?
Digitizers.
Water.
Yeah.
It's just water. And digitizers. Yes, we're going to be talking about the mostly about the digitizer today. We're going to talk a little bit through the layout of what an RF in signal would look like.
The digitizer is a big deal for us. This is probably the highest risk item that we had remaining on the detector. Yeah. So it's a big deal for it to be done.
A lot of time, effort, energy, thought. Choosing components. It's been absolutely insane.
Yeah.
The choices that 3-hour-long discussions and then revisiting a week later.
Well, I actually want to bring up kind of give a shout out to one of our engineers. Not Rob. This is a different anonymous engineer, although Rob did help. We were initially going to outsource the development of the digitizer. We were going to do it locally still in Cincinnati, but we just were running into manpower issues because we're a small company. And the digitizer is really, really hard to do, and it really has to be done right. It's the circuit board that takes the analog signal and converts it into a digital signal so our AI can see it. And that's where all the fancy, expensive stuff, like the analog to digital converter and the FPGA, that's where they all live. And one of our engineers stepped up and said that he would be willing to do it himself on nights and weekends just to make sure it was done right. And doing it like in-house with tight integration, talking to the rest of the team who's building it. So it was pretty cool that he pulled that off for us, and it works awesome.
He is incredible.
Yeah.
I mean, everyone who works here is incredible.
Well, not everyone, but I'm just kidding.
So to put up with? Yeah. But yeah, so let's dig into it. Let's go to the whiteboard and take a look at what.
Before we do that, let's just show real quick where it actually lives. So this is obviously Theia's motherboard, and the cool part about the digitizer is it's the first time that we've had a fully, it's a radar detector now. It exists as something that we can plug USB into. You got the horn, you got the RF circuitry, you got the digitizer, everything fits together neatly. This one right here I have disassembled just so I can kind of show you guys the stack up of it. But we've showed you the motherboard before. Every time. We've showed you the little SOM, which is where the AI lives. We've obviously showed you the horn. But what we haven't showed you is what comes underneath the horn. So we have a cutout at the base of the horn where there's 6 connectors. And we built a digitizer board that has to perfectly connect to all 6 of those connectors, lives in there, and then has to connect perfectly to the connectors on the motherboard. This one right here that I'm holding is actually just a dummy because I don't want to expose our real ones to static right now. But we have some B-roll that we're going to show you actually what it looks like here. But it's crazy to me that something this dense and this complicated can be pulled off, designed, mechanically integrated in really tight constraints. I don't know. I just think it's really, really cool. I love this stuff.
I'm super nerded out by that.
So,
I'm not gonna lie.
Yeah.
Cool. Well, let's head over and talk about the digitizer.
Sounds good.
All right, so we're going to start out here with these beautiful pictures of Theia internals here. Up top is the first picture that we're going to look at, and it talks about, well, John's going to talk about it here in a second, what each of the layers are. We have a beautiful color code here, and we're going to really dig into what the digitizer does, but we think it's important to show you guys like how our internal components are. I mean, we talked about being unbelievably like methodical and almost crazy as far as detail goes with this build, but you want to talk about the PCB boards and all that and how we laid it in?
We already kind of gave you a brief idea of what the digitizer does. I mean, the whole term digitizer kind of describes it. It takes an analog signal that comes into the horn, it turns it into a digital signal that we can analyze, whether it's with DSP and the FPGA or through the artificial intelligence array. So as Mindy said, we've got 2 things that I want to explain here. One is the actual, I guess you could call it the signal path or the flow, which starts really when like a radar is received and then kind of zigzags its way through all the different circuit boards and what we get with. And then I want to focus specifically on the digitizer itself, which is this illustration here, and explain why we built it the way that we did. So I guess let's get started with the radar detector. Yeah. Do you want to draw a little radar signal coming in to one of the horns?
I would love to. I should probably use this.
Yeah, use the analog, yeah.
about the color.
All right, so Mindi is Johnny Law. She's shooting with some nasty 35.5 low power Ka band. I think she's gonna get us. But Theia is watching. So we've got Ka band coming in here, and the first thing that it's gonna hit when it comes in through the horn is what we call the RF circuit board, or the RF board. And this is where all of your fancy things like the LNAs live. It's a very difficult circuit board to produce. There's a lot of specialty manufacturing that goes into it.
Have we seen a picture of that yet?
No, and we're not showing that off quite yet.
It
is done though.
It's very sneaky.
But
we can't just show everything all at once, right? It's gotta be.
It's not polite. Yeah.
It's not polite. Yeah.
But that's where a lot of the magic happens on the RF side, and that actually captures electromagnetic waves out of the air and converts them into almost electricity in a circuit board. So there's a connector that we have on the bottom of that board that signal can flow through, and it's a special connector. It has to be 50 ohms in our case of resistance. If you get that connector wrong, your whole signal chain is degraded. And then it goes into this middle board, which is a digitizer, and that's what we're going to talk mostly about today. The digitizer's function is to take that analog signal, which we represent with this kind of like a fuchsia or a magenta color, and turn it into a digital signal. Now, it's important to turn it into a digital signal because that's where we do DSP, or digital signal processing. You can't do DSP in analog. You can do signal processing, but you can't be nearly as flexible as you can. Our digitizer is where our FPGA analog to digital converter and something called the IQD mod lives. We'll talk about that later. So now Mindi's sneaky 35.5 Ka band is converted into ones and zeros, which come out of the digital connector.
I'm going to finish this.
Yeah. So it's at this point where it's now ones and zeros. It's digital. It's no longer analog. And then that goes into the motherboard where our main CPU and the AI live. So you can almost think of it like the FPGA can present a buffet or a menu of information to the AI, and the AI says, hey, I want a picture of the signal, or maybe I want to know power over time, or whatever it is. And because it's all been processed in ones and zeros, that information can be sent very quickly to the AI where it can make the determination. So that's kind of the high-level overview of the signal path in pretty much any modern digital radar detector.
That's awesome.
So
let's talk about, now we're going to take this digitizer here, this board, and we're going to do an overhead view of it. That way you can see kind of the meat and potatoes of what actually happens to that flow from this overhead view. I think it's important to see that.
Yeah. And this digitizer is an extremely, extremely difficult board to engineer.
Mm-hmm. Out of all things that we've engineered,
I would say the RF PCB is the most black magic, but I think this is very, very closely behind. The main motherboard, it's a breeze. Like any quality electrical engineer can pull that off. It takes a little bit more chops to integrate a very dense layout that has an FPGA with an ADC. There's a lot of chance to mess up the circuit where noise can creep in. And
that's also kind of a cool point. So we're doing so much on this digitizer board, right?
Yeah.
Real quick, the notch outs in the bottom of the horn when we're talking about like fitment.
Yep, mechanical.
Yeah, I think like to make the footprint of Theia as small as possible and as compact, right? So it's not this massive spaceship,
yep.
Right? To be able to, to have thought of building the digitizer.
It's very tricky to get everything to line up perfectly.
I guess it's things that I would never have
also
thought of that.
For thermal to be, we wanted all these to be thermally coupled to each other. And that's so the circuit board here is the same temperature as the circuit board here and is the same temperature as the horn. So we built things in a way where they would be thermally stable and not have different rates of contraction and expansion. And I mean, it's incredibly complicated.
Also, real quick, and I might be going off a little into the weeds, but as far as external heat and temperatures or the amount of heat that they emit here, have we thought about that?
Yeah, I mean, we've taken thermal considerations in from day one. And
it's a common question that I see sometimes in FAQs.
For sure. I mean, you got to realize that there's a lot of things that function as tremendous heat sinks in here, from the horn, which is a massive chunk of metal, all the way to the copper ground planes that are on the back of these circuit boards. It's a really conducive environment for transferring heat from the processors all the way to the outside aluminum case, which aluminum is also a great heat sink. So we've definitely taken thermal into consideration.
I didn't doubt you for a second. I just wanted, the people want to know.
Yeah.
Awesome. So let's show what the RF in looks like down here.
Yeah. So having a digital radar detector, it allows you incredible flexibility, especially if you have a big FPGA. I think this is one of the coolest things about radar detection, I guess radar detection design, and I feel really privileged to work with people that can conceptualize and understand and actually make this come to life. So starting with your RF in, this is that 35.5 Ka band that Mindy's shooting, and it's coming off of this connector here. It's coming out of the horn. And the first thing that it's going to do is it's going to go into, the technical term is a monolithic IC. It's a chip, and we call it our IQ mod. What that does is it takes this RF in signal that has a lot of different information embedded in the signal, whether it's phase noise. We talked about how we can look at the phase of signals. Or
more on that later.
Yeah, or several other pieces of information. And it can extract the useful features that we need from it and separate in phase and out of phase signals. So it kind of organizes and down converts the signal to baseband at the same time. This is something that traditionally detectors needed 2 or 3 mixing stages to do. This is why we're kind of not a traditional super heterodyne triple conversion receiver as the Escort is. With traditional radar detectors, you need to mix your initial signal coming in with an LO, mix it again, and then mix it again. We don't need to do that. We have one mixing stage in our RF circuit board, which allows us to only have one synthesizer, which means we can spend a ton of money on it to get really, really good performance. And this magical little chip takes that pretty high frequency signal relative to other radar detectors and can just down convert it, extract phase, and present it in a really clean way to the ADC all in one step.
And notice that then that's why you have 2 lines here.
Exactly. So these represent, this is a signal where you can see phase on it. And it's important to note that our ADC has 2 inputs. So it can actually look at both of these at once.
Very cool.
So now we have an analog signal that's a little bit more organized. It's been demodulated down to a lower frequency. And it enters the analog to digital converter. This is one of the most important components in any radar detector. So when you are doing a process on a signal, there's always going to be loss. Stuff just goes wrong. I mean, noise creeps in, or if you're using a cheap part, you can't see it very well. And if you use a low quality analog to digital converter, that loss can never be gotten back anywhere up the chain. This is the first time where the signal switches from analog to digital. And if you do a poor job converting that, it doesn't matter if I put a supercomputer behind it. You're never going to be able to see the signal with good fidelity. There's a couple of different things about ADCs, as we call them, that are important. You can kind of even just look online and see what the specs are. It's like horsepower in a car or processing speed in a computer. And I think that the 2 most important ones for our point is how many bits it has, and then what its sample rate is. To give an analogy about the importance of bits, this is how much dynamic range the ADC can see with. It's kind of like the difference between looking at, if I have a foot, right? You got 12 inches in a foot. You could say that that distance has 12 steps that make up that foot. But what if you want to look at 1.75 inches?
I can't.
If you only have 12 steps, or you can only look at 1 inch at a time, you can't see with that good granularity. So ADCs get very expensive the more bits that they have, because that represents how fine you can see.
And there's been a lot of talk about which ADC we're going to choose and what sample rate.
Yep.
And I mean, many conversations
so
around this.
Most radar detectors that have ADCs in them, or have premium ADCs, I should say, are 8 to 10 bit. We're actually using a 14-bit ADC. There's no other radar detector on the market that has an ADC with that many bits. It's definitely, we have the most dynamic range in our ADC. The second point of an ADC is the sample rate, or how many times per second it can sample a signal. And I'm going to super simplify this to make it, this is not technically accurate, but for the way that radar detectors use it, it is. Usually that is also correlated with how wide of a frequency span your radar detector can look at it once. So if you
like last week's video, right?
Exactly. So, you know, Escort looks at maybe, let's just say they look at 10 megahertz at a time. Their ADC would typically be a multiple of 10. We wanted Theia to look at as much bandwidth as possible at the same time, which is better for filtering out blind spots or detecting multi-radar. So we used a 60 megasample ADC. Getting a 60 megasample 14-bit ADC is incredibly expensive. I think this ADC is about $50 a pop, but it's worth it because it's kind of the backbone of your whole detection system. I mean, garbage in, garbage out, and our AI could be amazing, but if it can't see the signal, it's not going to work.
And then as far as sample rate, I want to make sure I'm getting it right. So, example, if Thea is looking at like Falcon, she's going through her library of bajillion items, right? Not really bajillion, but all these items that we've trained her on. Does that mean how many pictures she can look at one time?
No, not quite. It means when the AI draws, let's say you see a signal.
Yep.
Let's say that the radar detector sees a signal and it knows that it's modulated or wide.
Okay.
Right? What it would do is determine how big of a snapshot of that signal you can take and send to Ray.
Perfect.
So if you don't have an ADC that can look at a lot of bandwidth at once,
that's right, because we're above.
Exactly. I mean, I'm just going to illustrate it quickly. So let's say that you have a BSM that looks like this. Mm-hmm. If you have an ADC that can only see 10 megahertz at a time, all that you can do is take a picture like that and send it to your AI.
60.
If you have 60, you can take a picture that big, which means your detector is going to be much more able to tell what the difference is between those two wide signals.
Such a beautiful drawing. Thank you.
I apologize for my horrible art skills.
Yeah. Thank you for breaking that down, though. I appreciate that. Cool.
So anyway, we've established now that we've got a really, really high quality analog signal, and now it's being turned into a really, really high quality digital signal. What's next? And that's these incredible devices called an FPGA.
Field Programmable Gate Array.
I taught you well. In reality, Rob taught me well, so I guess it's. But these things, you've heard me talk about them before, and they absolutely blow my mind. We're going to have a whole separate video just on FPGAs, so I'm not going to go into an incredible amount about exactly what they are or how they work here. But the important thing to know is that it serves two purposes. The first is to simply ingest the tremendous amount of data coming off of that ADC. Think of this ADC, because it's a high sample rate ADC, as kind of like aiming a fire hose out of a fire truck and just turning up the water to max. If you can't drink out of a fire hose, I mean, you're going to get blown away.
Totally.
And if we didn't have a special device that was capable of doing that, then we would never be able to make the connection between the AI and the digital information coming out of the ADC. It just wouldn't be able to handle it.
Smart.
So that's the first function of it. And the second function of it is that it can do digital signal processing basically for free, time-wise. So this is not like a traditional computer where maybe it takes 15 milliseconds or 20 milliseconds to do DSP on a signal. An FPGA can do it in microseconds. So we've programmed a bunch of different DSP engines into the FPGA to present that menu of options to the AI. So if the AI sees that there's a signal, it can ask the FPGA to present that signal to it however it wants. Maybe if it sees a CW signal, it can ask us to present a very zoomed in close-up signal. That way we can see it better.
Totally.
That's kind of how Valentine looks at it. Mm-hmm. But maybe if it's a frequency modulated or camera or BSM, sample, it can look at a huge one. So having this flexible system where all of the components are working together to say, hey, what are you seeing? I see this. How do you want to see it? Okay, here you go. With no lag time is pretty incredible. And it's something that we can continue to update for a decade down the road. I mean, this FPGA is 14 times the size of the one used in the Valentine 1 Gen 2, and it's more than twice the size of the one used in the Escort Max 360. And because we have dedicated processors for everything else that's not DSP, we're not wasting resources in the FPGA with normal functions of a processor. So this chain right here on the Digitizer is what is going to be responsible for a tremendous amount of Theia's performance, and it's completely unparalleled and unprecedented in the radar detector industry.
Then the signal comes out and is then going to go down to
the AI.
The
Yep.
AI.
And the AI can have.
And now she's got.
She can have whatever she wants.
Yeah, it's like this FPGA sounds like it's got this amazing like menu of like lobster thermidor and all these wonderful things instead of just like a hamburger Happy Meal.
With an FPGA, and I want to be clear, this is not just Radenso's FPGA. Like if Escort found a programmer that could do FPGAs, they could do the exact same thing. They couldn't fit as much as we could, and they don't have as much processing power, but FPGAs in general are so amazing because if you take an analog detector, you can simulate that entire detector in an FPGA. If Escort wanted to process signals exactly the same way as, I don't know, the original Redline did, if they could do that in the Max 360 with the FPGA, they would just have to program it. We could emulate a Pro-M in here if we wanted to, or we could emulate a Valentine 1 Gen 2 in the FPGA. Plus, we retain the flexibility of being able to do it however we want, instead of an analog design, which is fixed to one way and optimized to one way.
I think that kind of like to put a bow on it, like it's having killer hardware, but it's also the team behind it of engineers.
You have to be able. This is the most challenging programming software job in the entire radar detector.
Yeah.
Any quality programmer can do the user interface, can do the vast majority of it, but finding somebody who can do quality DSP in an FPGA, most of those guys are working at Northrop Grumman and companies like that.
That's awesome.
So.
Well, thanks for the breakdown. I appreciate it.
Yeah.
I got a lot out of it. Hopefully you guys did too. Let's head back to the table.
Perfect.
So thanks to your wonderful sketches and knowledge that you have, we're able to talk about what the flow of the RF in signal looks like to the digital out that goes to the AI. Hopefully you guys found that like super beneficial. I mean, it's interesting talking about all the components like individually, but actually for the first time talking about like how it flows.
Yeah. The first time as a company that we had everything together, generated a signal and saw it flow all the way through and saw the output looking like we expected, that was kind of a big, fist in the air cheering moment. I mean, at that point you have yourself a radar detector.
That's awesome.
We've done so much development on separate development boards and separate using breakout boards and all that kind of stuff, and we knew theoretically it would work, but the first time you actually test your assumptions and it works is kind of a huge sigh of relief.
Yeah.
And we did it all in-house. It's really cool.
Homemade with love in Cincinnati.
Yep.
It's awesome. Well, thanks for tuning in, guys. If you have not yet subscribed, hit the little button.
Please do.
Yeah, and enable notifications. And again, as always, we appreciate you guys' support and the love for us. We feel it. And thanks.
Definitely.
Catch you guys next week.
Take care, everyone.
Bye.